Hello everyone. This video is about quick read codes or QR codes. We'll be walking through the steps involved in this decoding process. We'll take a QR code and then we'll manually decode it by hand. So for that, first we'll be covering some basics to go to the decoding phase. First we will be seeing the QR code structure, and then we will see the QR code storage, some basic things in the storage, and the various error correction levels available. Then we will see what is masking, the masking patterns, what are the error correction levels, how are the error correction levels and masking patterns are stored. Basic things we'll see. Then we'll go to this decoding part. So let's begin. Now we'll look at the QR code structure. First we will see the corner features. These are the quiet zone, finder patterns and separators. So first we'll see the quiet zone. The quiet zone is a green color region here, just surrounding the QR code. Its purpose is to separate the QR code from its surrounding. And next we have these position squares. These are the three squares present at the corners of the QR code. These squares helps the scanner to distinguish a QR code from any other pattern of random black and white squares. And adjacent to this position squares, we have this vertical and horizontal white color strips. These are called separators. So what it does is it separates the position squares from the format information, red color part, and the version information. So format information contains the very required error correction level and masking pattern info, which is very much required when we want to decode the code. And the version information gives us information about the size of the QR code. So next is the alignment patterns. Alignment patterns are similar to position squares but are smaller than that. These are present symmetrically about the diagonal. That is, if you imagine a diagonal here as your line of symmetry, you can see these alignment squares are symmetrical about the axis. Its purpose is to see to that the distortions are detected and corrected. As this QR code is printed on a physical medium like paper or cardboard, as time passes, certain regions of the code will lose its color, so distortions occur. So we need these alignment squares for the normalization so that we can correct these distortions. Next we have this timing pattern. This timing pattern is this alternate black and white square. This pattern is timing pattern. It supports symbol density and helps to determine the version or size, and provides positions for determining row or column coordinates. It basically gives the scale of the QR code, like provides us information about how big each and every cell in your code is. Then next is the left out part, which is your data, the gray color region. It is where your actual message goes. Along with it we have error correction code words also. We require these error correction code words to retrieve your data back when your QR code is damaged, and the system uses the Reed-Solomon error correction algorithm to do it. Oh, that's it for QR code structure. Now we look at the various QR code versions. We have this version 1 here. It's 21 cross 21, which means we have 21 rows and 21 columns. Then this is version 2, 25 cross 25. Version 3 with 29 rows and 29 columns. And there's version 4 and version 10. Next we have even bigger versions. This is version 25 with 117 rows and 117 columns. And we have this version 40 with 177 rows and 177 column. This is the biggest version of QR code available. And then we look at the QR code storage. The amount of data that can be stored in QR code depends on the data type, the version of the QR code, and the error correction level. So we'll look at the error correction level in the next slide. As you know, if the version is bigger, then we have more space, so we can store more data. And then it also depends on the data type. So this table here shows us the maximum storage capacity, maximum character storage capacity for version 40 and error correction low QR codes on various input modes. We have numeric only mode, in which we can store only numbers, and we have alphanumeric mode, in which we can store numbers, alphabets, and also special characters. And we have binary mode, in which we will be storing zeros and ones. And we have kanji or kana mode. This is the Japanese language. So the next column here tells us the maximum characters that we can store in this version 40L QR code on each individual modes. So if we go for numeric only mode, we can store about 7,000 characters, and as we go down this table, maximum characters decreases. Scanji Arcana, in that language we can store only about 1817 characters at max. And this next column here tells us the number of bits required to store a character in each and every mode. So for binary data, in the binary mode, to store a single character we require 8 bits. And one more thing, the maximum storage capacity occurs for version 40L QR codes. So this L is the lowest error correction level. It's already said the error correction code words and the data code words are your message. Both of them share the same space. So if your error correction level is low, which means there will be lesser number of error correction code words, so that more data words can be packed in that space, so that your storage capacity will naturally increase. That is the reason why we have maximum storage capacity for version 40 and lowest error correction level, low QR codes. Now we look at the QR code encoding. So the encoding process requires the format information. It is the same format information we require for decoding also. So this format information records two things: the error correction level and the masking pattern. As you can see here, in the format information, the first, that is from the bottom to top, if you see the first 5 bits, in that the first 2 bits are the error correction, it denotes the error correction, and the next 3 bits denote the mask pattern. So if you have a dark and a dark square, so before that, a dark square corresponds to 1 and a white square corresponds to 0. This is how your data is stored in the binary form in the QR code. So if you have 2 dark squares, which means 1 1 error correction level low, and then if it is 1 0, an error correction level medium, and if it is 0 1 error correction level quartile, and then if it is 0 0 error correction level high. So this table shows you the percentage of code word, that is 8 bits, 8 squares in your QR code together make a code word, and the percentage of code word that can be recovered. So if you go for a higher error correction level, you can get 30% recovery, and lower error correction level gives you 7% recovery from a code word, from a single code word. And these are the 4 error correction levels. And next comes the mask pattern. Here you can see the various mask patterns used. So if our data is 1 0 0, then we have to look for that particular mask pattern, 1 0 0. This is your mask pattern used. And here I variable denotes the row number and J denotes your column number, and these mathematical formulas are used to generate the mask pattern. So what is this masking, mask patterns and all? Masking is used to break up the patterns in the data area that might confuse a scanner, such as large blank areas or misleading features that look like the locator marks. Locator marks are alignment squares and timing patterns, position squares, etc. So the thing is, our data is not directly placed in the QR code. We place our data and then we mask it. How we mask is, let me explain to this illustration here. So this is your unmasked version. Let us suppose in our unmasked version we have dark color squares in these 3 places, and this is our masking pattern. So in masking, modules corresponding to the darker areas of the mask are inverted. So imagine that we are placing this sheet of paper above this sheet. Then in your mask pattern, the modules corresponding to dark squares, so that those regions should be inverted in your original data. It is here this square is dark and this square is dark. So in your data, we change this white color square to black, that is we paint it black, and then here we change this black color to this region to white. We don't do, it's already white, and the other two squares in your data are not affected because it is white in your mask, so they are not affected. This is your masked QR code. data, which you see in your QR code. So this is how masking is done. And the mask pattern are defined on a grid that is repeated as necessary to cover the whole symbol. Now we'll continue the QR code encoding. The format information is protected from errors. The BCH code, like I have no clue what is a BCH code, and 2 complete copies are included in each QR code symbol. As you can see here, this red color region is the format information, and we also have this duplicate format information here, a copy of it. In a similar way, the format error correction and its duplicate copy is here. Look in this picture, we have code words. So these numbered blocks, these numbered words or code words, D20, E1, E27, these are code words. So code words together make a code block, and 8 bits, there's 8 bits, 8 squares together make a code word, and a group of code words together make a code block. As you can see here in this QR code, we have 2 code blocks, block 1 and block 2, and these code blocks contain data code words and error correction code words. They contain both. As you can see, block 1 contains data code word from D1 to D13, and block 2 contains data code word from D14 to D26. If you see here, we have D1 here and D14, D2, D15. So you have to observe the way how it's arranged in this. That is how the code words are arranged. The code words from different code blocks are interleaved together. It is not like D1, D2, D3 up to D13, then D14. It is interleaved together. We interleave this like this to prevent the loss of data when a QR code is damaged from one block itself. Doing this, we don't lose much data from a single code block, so that we can apply this error correction and retrieve the data back. And we also have error correction blocks. These error correction blocks, as already said, are used by the read, solve and error correction algorithm to retrieve the data if your QR code is damaged. And these arrows indicate the order in which we have to read the data from the QR code. These are the various shapes, and 1 is the most significant bit and 8 is the least significant bit, LSB and MSB. So you always have to read the bits from right to left. So you can see right to left. So you have to read like this: 1, 2, right to left, 3, 4, 6, 5, 7, 8, like that. And this arrow is till the order in which you have to read. If you consider this downward arrow, you should read like 1, there is no left. Okay, 1, 2, 3, 4, 5, 7, 6, 8, like that. You have something which changes direction, like the shape, and you have to follow along the arrow and then follow the right to left rule. It is 1, 2, 3, 4, then 5, 6, right to left, then 7, 8, like that. In a similar way, if your data is arranged like this, then you have to follow down here, then go to 8, which is placed above the format information, and that is how you have to read your QR code data. We'll be using this technique when we encode our, when we decode our QR code. After every indicator that selects an encoding mode, so you have this encoding mode block, which will give us the information about the encoding mode, is a length field that tells us how many characters are encoded in that mode. And the number of bits in the length field depends on the encoding and the symbol version. So the length field tells us in that particular encoding mode how many characters are encoded. The number of bits in the length field itself depends on the encoding and the symbol version. So this table tells us the information stored in our indicator block. So if it is 0001, which means the mode used is numeric encoding. If it is 0010, alphanumeric, and then if it is 0100, byte encoding. And one more thing here, if it is 0000, then it is end of message, which means our all data code words are over and we have reached the end of message. And this table here tells us the number of bits in the length field, and as it is mentioned here, it depends on the encoding and the symbol version. So if we go for numeric encoding, and choose a version 1 to 9 QR code, then we'll be having 10 bits in the length field. Then if you go for alphanumeric encoding and version 27 to 40 QR code, then we'll be having 13 bits in the length field. Similar way, this data is for various encoding modes and various versions. This is a QR code, and we will now decode the QR code step by step. So first, this region here, this region is the format information. From bottom to top, the 5 bits, 1, 2, 3, 4, 5, I have copied the bits and pasted it here for our reference. See this 1, 1 here. The first 2 bits are the error correction level 1, 1, which means error correction level low. So this QR code has this lower error correction level, and the next 3 bits tell us the masking pattern used, and we have 1, 1, 0, which means we have to search for the pattern here. So yeah, we have it here, 1, 1, 0, which is this pattern. So first what we should do is we have to generate the masking pattern to cover the entire QR code symbol. We have this masking pattern that is ready to cover our whole QR code. In this picture, if you see, the yellow color region is our data, and this brown color region is the indicator block, and this will tell us the encoding mode used. And this blue color region is the length field, and this will tell us the number of characters encoded, that is number of characters in our message in that particular encoding mode. So first we will unmask the QR code, then we will be looking at these two, encoding mode used and the number of characters in our message. So what we do is we take our original QR code, this original QR code, and we place our masking pattern on top of it, and then the dark areas, the areas in our QR code which correspond to the darker areas of the masking pattern are inverted. That is how we unmask the code. So as you can see here, these two regions. Originally this is a white color block square, and this is a dark square. So if you see in this becomes dark and this becomes white. We have inverted the bits. In a similar way, we do this for all the data region, that is all throughout the yellow color region. We invert the bits according to our masking pattern. After we invert it, after we have unmasked our QR code, we get the data. We see the actual data here. This brown color region, as I already told, is the encoding mode. So the encoding mode, we have to look from right to left. So 0, 1, 0, 0. We will see here, copied and pasted the region for our reference. So this brown color region tells us that 0, 1, 0, 0. We'll see what encoding mode it is. 0, 1, 0, 0, byte encoding. So it is binary data. And then we'll see the length, number of characters. 0, 0, 0, 0, 0, 1, 1, 1. So 1, 1, 1 is 7 in decimal. So we'll be having 7 data blocks. Data 1, data 2, 3, 4, 5, 6, 7. And after the 7th data block, we are seeing this 4 empty squares, which is 0, 0, 0, 0, which means 0, 0, 0, 0, end of message. We have reached the end of our message, so we have done the encoding process. You can compare it with this diagram if you want. See, in this length field, the 0, 0, that is white, 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 and then we have 3 black squares. Always go from right to left. So 1, 1, 1, and see the data number 2, which has a turn in it. Like the arrow goes here, it comes like this and goes down. So you have to go from right to left. So we go 0, 1, 0, 1, 0, 0, 1, 0. In the next slide it's shown clearly. So this is our encoding mode, and this tells us the data fields, number of data fields. And then this one's our first data block, this one's second, this one's third, fourth, fifth, sixth, and seventh, and finally we have our terminator block. Now what we do is we convert the binary information to the decimal form. It is this particular 1010001 corresponds to 81 in decimal. In a similar way, this is 82, and this 32 is, this thing is 32, 2 to the power 5, and this is 67, 111, 100, and 101. Now what we do is we take an ASCII table and then we compare the decimal with the character to find the character. So 81 corresponds to Q. You can see through the table. 81 here corresponds to alphabet Q, capital Q, and 82 corresponds to R. The similar way, 32 is blank space, 32. Then 67 is 67 is C. Like that we decode the message, and the message stored in our QR code is QR space code. That is the message we have encoded in the QR code. If you want to verify it, you can verify it for yourself. Pause the video here and take your mobile phone, smartphone, and then scan the QR code. That you will get the QR code message displayed. So that is how we encode it manually by hand. And there are also QR code extensions. We require these extensions to store more data. To increase the data density, we add colors. So the researchers have proposed a new high capacity colored 2D code. It builds upon a QR code basis for preserving QR code robustness to distortions, and use colors for increasing data density, storage density, data density. It is still in the prototyping phase. They also included colors, and if you include colors, it requires addressing additional issues. For example, in your normal QR code, that is the black and white QR code, we have to worry only about the brightness information. That is, if it is too bright, then it is white. If it is dark, then it is black. It is easy for us to distinguish between a black square and a white square, even though sometimes the QR code fades out as it is printed in a paper or cardboard usually. If you go for this colored QR codes, we have to cope with chromatic distortions. It is, as time passes, the color may fade, and the information, the scanner might interpret it to some other color. It is, for example, if you see here, the red color might fade out due to sunlight, and then it might turn into pink. So the scanner might get confused. So that we have to ensure that we have error correction patterns for this to correct the distortions, chromatic distortions also. So in order to ensure adaptations to that chromatic distortions, we have to make sure that we use an additional field. It is like your format error correction. To be more clear, it is like your error correction code words, which will account for the damage done to your QR code to retrieve the data back. And similarly, we want to include an additional field for accounting for the chromatic distortions also. So that's all for the presentation. Thank you for watching, and make sure you hit the subscribe button, and I will see you in the next video.